up, dudes? All right, here's how the thing is going to work. I'm going to record just kind of a demo for you to show you folks what you folks are going to be doing in this lab. I want you to conduct this lab. Try to be clean. It's got a lot of like water that we're going to be using, and I don't want you to spill stuff. And also clean up after yourselves. That's super important in this lab. I will try to do more explosive labs with you, I promise. And hopefully we can do stuff where we like mix chemicals and do some titration and that kind of stuff, and work with even hydrochloric acid, which will burn a hole through your hand if you're not careful. But until we get there, I need you to be careful with these things, and I need you to learn how to correctly use chemistry equipment. So, also, during your experiments, I don't know if you've noticed, but I'm kind of a stickler for accuracy. I'm kind of a stickler for getting every single number correct, right? That was the whole thing about significant figures and significant figures and uncertainty in your measurement and all of that kind of stuff. Well, now you're going to learn how to apply all of the things that we learn in chemistry lab. Cool? So here's what we're going to do today. We are going to measure the density of some unknown rock. Actually, I'll tell you what it is. It's called magnetite. And it is a special rock. If you break it up into really small pieces, I noticed that I couldn't plug in my power cord for the Mac computer because there was a little piece of this thing stuck, like a magnet to this thing. And then when I walked by Sarah's magnets over there, it actually, this thing is a magnetic rock. It's really interesting. But it has a very specific density. And so what we're going to do is I'm going to ask you to calculate the density of this thing as accurately as possible, and then figure out your percent error, which is something I don't necessarily know if all of you know how to do in a lab. So this is my opportunity to teach you. Cool? All right. First thing is a pre-lab. And I want you to do the pre-lab, even though technically I should have just emailed this out to you and had you do the pre-lab at home. I'll show you how to do it. It's very quick. It's very easy. What you're going to do is you're going to look at a thermometer. Someone pass me their thermometer. All right. Let's do the pre-lab together. Look at your thermometer. It goes in increments of what? Tens, hundreds, ones? What are each line? What is the scale? Each line represents what? 1 Celsius, 10 Celsius? What is that?
10 degrees Celsius.
Nope. 1.
Oh, each line.
Yeah, can you see a thermometer and anything? All right. So, do you guys have a thermometer back there? There's one right inside that little box over there. Perfect. All right. So, if I can measure something up to 1 degree Celsius, let's draw a thermometer. This represents 1 degree Celsius. Then how do I write down my temperature? Like, what happens if the red line were right here? And say this is 0 degrees Celsius. There would be a little ball right here. And this thing would kind of come out like this. There we go. There we go. Now it looks like a thermometer. Actually, it looks more like a pipe. There we go. Now it looks like a thermometer. What is this value right here? 3.5? You say 3.5? Okay. Are you allowed to write? Can I make it maybe like 3.65?
Is that what it is?
Well, can I?
No, it's not that accurate.
Right, it's not that accurate. You can only write down one place past where you measured it, or where you can definitely see. Because this is the smallest actual thing you can see. I can guarantee tell you it's 3, right? It's at least 3. Now the second one is your guess. The next number is your guess. And is 3.5 correct? Sure, it could be correct. Is 3.6 just as correct? Yes, because that's your guess. You're allowed to guess that last digit. But I can't write down 3.65 because that would be like doing a double guess. Does that make sense? So you're allowed to write down one digit past what you can see. And That one digit is actually your guess. I'm teaching you guys at this point. This is your uncertainty in your measurements. We cool? Awesome. So that's the answer to part 1 in your pre-lab. Choose a decimal or choose a temperature between 0 and 100 degrees Celsius. Go. I'll choose one. 26. 26 degrees Celsius. That might be a good one. All right. Now, density of water changes depending on the type of... Am I even recording this? All right, yeah. Density of water depends on the type of the temperature and the pressure that you're at. So what I did was I said, I looked up what is the density of water at different temperatures and pressure calculator. I just typed that in. The first website I got was this. And so you put in the pressure that you want and the temperature that you want. So at 26 degrees, and the pressure, the barometric pressure on Honolulu, I think is 29.89. That's not a number I expect you to memorize. I looked it up earlier. Cool? So you guys can put that in. That density is, the density of water is 998.08, all of that kind of crazy amount of significant figures. And I guess you could write that down if you wanted to. Kilograms per meter cubed. Got it? So that's part 2. Cool? I'll let you do part 2C on your own. All right, showing you the lab. Let me run through it real quick, and I will show you what to do, and we'll go through this. So, first thing I want you to do, I want you to measure the volume of a graduated cylinder. This is called a graduated cylinder because it is cylindrical. It doesn't look like a cup which has tapered ends like this. The graduated cylinder is, you can measure the diameter like that. You can measure the height like this. And you basically get the height of, I asked you to get the height of 500 milliliters. Tell me what that is. And from that, you could calculate the volume that's inside this thing, right? Do you guys know the equation? What's the equation of a circle? Starts with pi. Pi r squared. Good. The equation of a circle is pi r squared. So if you get the diameter, you can tell me what the r is, right? You use pi r squared to get the area of this. And to get the volume, all you do is multiply that by whatever height you're talking about. Cool? So you can tell me what the volume is by actually measuring this. And that's what part 1 is. Part 2 is, what I want you to do is measure, essentially I want you to get the density of water for me. So I think what I asked you to do is measure here's a scale. Measure the empty 100 milliliter graduate cylinder. Done. Write that down. Then fill this thing up with water somewhere between 50 and 100. Measure the mass. From that, can you calculate the mass of water that you actually just put in there? What would you do? You subtract it. Cool? And then you can also read the volume. Look, it's there. Cool? And then you can tell from that, you can tell the volume of water you have, and you have the mass of the water. You can calculate your density. Cool? What I want you to do is figure out what the density of water is for this particular water. The last thing is I want you to find the density of a rock. Now, hopefully your rock will fit into something like this. Half of yours won't. I'm sorry. I couldn't find small rocks. I've got big rocks. So some of you might have to use this. The bigger one. What I would do is I would take this water from here, since you already know the volume of that water, and you know it pretty accurately from here. You can just pour that in here and then put the rock in and figure out the volume of the rock. I think before you get the volume of the rock, get the mass of the rock. Just put it on the scale. You'll be able to find the mass of the rock. And
why are we using these specific rocks?
Because these are all the same rocks. I was actually thinking about giving everyone different rocks because there were some rocks over there that I wanted to get the densities of, but I think that it'd be good for us to get the same rocks because this will give me an opportunity to teach you about standard deviation later on. So we're going to get into that a little bit later. And to do that, we all need to take the measurement of the same kind of type of rock. Okay? What is the advantage of using maybe the medium-sized one over the big one? What do you guys think? Huh? The smaller one's more accurate. The lines are closer together. These ones have bigger lines. Cool? So I think I saw a short, fat graduated cylinder back there. One of you folks can use that if you got a big rock. So that might work for you folks because that would be accurate and you'll be able to do that. Be careful when you drop this thing in here. What I like to do is I kind of drop it in here, put my hand over it like this, and drop it because what happens when you put the water, or when there's water inside, it's all going to splash out, and then that's going to throw off all of your measurements as well. We cool? All right, the last thing is this. In order to calculate the percent error, what you're going to do is you do this. Let's say that I measure that when I calculate out the volume of this thing, I measure it to be 988 cubic centimeters. That is the volume that I calculated in part 1. And I want to see, well, how inaccurate am I? How far off am I from the real answer? Let's say that the real answer was supposed to be 1,000 milliliters. By the way, just to let you know, I can interchange this with. Any problems with that? You don't want to fight me on that? All right. Because 1 milliliter is defined as a cubic centimeter. We good? All right. So if I measured 988 and the actual answer is 1,000, then here's how I figure out the percent error. I just take my number, subtract 1,000, and divide by 1,000. So you take what you measured minus what it's supposed to be, divide what it's supposed to be, and then you take the absolute value of that. Because you only want a positive percentage. Someone used their calculator. What is 988 minus 1,000 divided by 1,000? Actually, what's 988 minus 1,000? Negative what? 22? Divided by 1,000? Well, that's just 0.022. So my percent error is 2.2%. Cool? Does that make sense to you, everybody? All right, have at it then. Oh, and I think somewhere in the directions, I want you to measure the temperature of the water. Because the temperature that you read your water at is going to change the density of the water that you actually have. Does that make sense? Yes? No? Yep. And I showed you guys just on that website how to look up the density of water. You're going to need to get your water from back there. Here's an extra rock if someone wants. It fits in the small one. Did I just tell you, you measure the... Oh, for the pre-lab?
Yeah.
Yeah, you can write anything you want. I just went through it with you with my numbers. 1,000 minus 980 is 12. How come you told me 22? Making me look like an idiot. I don't do good math, by the way. All right. If you need, I think that we forgot to give you guys meter sticks, so you're going to need to grab that. I'm going to be walking around to help you out. I will probably also be recording videos on this side for the rest of the class to use. We're going to hold chemistry labs. And like I said, were you here when I gave my little spiel? I want to get to labs where we get to blow stuff up. Not blow stuff up, but maybe mix crazy chemicals where you have to be crazy careful, because if not, you're going to burn a hole through your hand or anything. Those are the fun labs for me. I don't have the chemicals. I will try to figure out the chemistry so that I can even maybe do MacGyver style, where we'll do a house. Oh, you don't even know MacGyver style. All right. Oh, you do? Okay, good. You got the reference. Where we'll get to do stuff where, like, it's home stuff. Anyway, finish off your lab by 3:30, so you have about an hour, and then we'll get out of here by 3:40 when we clean up. Cool? All right.